Hello, it's great to be with you. My name is Cheryl Desha, and I'm an environmental engineer at Griffith University in Brisbane, Australia.
And I'm Samantha Hayes. I'm a consultant and researcher in sustainable construction and biomimicry in Brisbane, Australia. And we wanted to take a few minutes today to run through with you a few key ideas around biomimicry. So, starting with what is biomimicry, then starting to look at what applications there might be for biomimicry in engineering and how those applications and ideas might benefit the design of our cities. So, biomimicry as a term, the word comes from bios, meaning life, and mimesis, meaning to imitate. And it's a design discipline that really looks to draw out nature's best design ideas and concepts and apply them to human design challenges. And it's based on the premise that life on Earth has existed for almost 4 billion years, and that during that time, organisms and ecosystems have been testing and adapting and refining design strategies in response to a lot of the same challenges and operating conditions that we're now trying to address in our design and engineering solutions. So things like climate change, resource scarcity, a whole range of different operating constraints that we're designing for now. Different organisms and ecosystems have already had to adapt their design approaches to those various challenges. The idea is that we can essentially take a bit of a step back, adopt a bit of humility and look to those systems and see where we can learn from them. If we were to squeeze the history of the universe down into one calendar year, we would see that life on Earth appeared around September. Humans arrived at 8 p.m. on New Year's Eve, and the first human settlements arrived about 20 seconds to midnight.
So what we'll look at now is the applications that biomimicry has to engineering and what examples we can learn from in terms of infrastructure design. So we'll give you a brief explanation of learning from nature at the level of form, process and system levels, and think about what that means for infrastructure and design. Let's think about this in relation to a popular example of the Shinkansen, or the bullet train in Japan, and how that was able to benefit from a bit of creative thinking on the part of the engineers. So if we take the Shinkansen, it was the fastest train in the world at the time of its design and production, going at 200 miles per hour. But the air pressure changes as the train would pass through tunnels caused such a big thunderclaps or pressure differences that the residents up to a quarter mile away would complain and the windows would smash. Not a really great solution for long term. However, the train's chief engineer and very creative fellow was actually a bird watcher, and he asked himself, is there something in nature that actually travels really quickly and smoothly between two very different density mediums? And with that in mind, they were able to model the front end of the Shinkansen on the kingfisher bird, which dives from the air into bodies of water with very little splash to catch fish and then emerges to perch on a branch, quite happy and able to do it again. So really quite energy efficient. They were able to achieve a noise reduction and avoid that pressure change situation. They actually used 15% less electricity as a result, and the train moved 10% faster. So a really great win-win-win solution as a result of some creative engineering that took inspiration from nature. There are other examples around tree and bone growth with structural optimization. You might look at oyster shells with some tough structural composite materials, the spider web around concrete reinforcement and configuration, and even leaves and insect wings around cantilevered sheets.
That's such a good example, Cheryl, because it shows how simple some of these ideas and applications can be. So that concept, that functional performance outcome, has already been refined over tens of thousands of years, and we don't need to now go and redo that work. We can look to where those design parameters have already been optimized. Similarly, so beyond that form level, where you're looking at the shape and the form of an organism or part of an organism. The next level then is looking at process. And so that's drawing on processes that we see in natural systems. Things like biomineralization, self-renewal and self-repair. So those are ideas, for example, of self-renewal and repair. They're things that we see everywhere in natural systems, but we really very rarely see in engineering. So how can we start to design infrastructure and materials and products that can internally sense vulnerability and damage and then initiate self-repair processes? That sounds like such an exciting concept for our built environment, and it's something that is really quite standard within our natural environment. There's a lot of work underway at the moment looking at materials like concrete and asphalt and trying to develop these self-repairing materials so that moving forward, the way that we operate and maintain infrastructure in our cities could really be quite dramatically different. Similarly, at the system level, there's a lot of work underway to look at how we can learn from ecosystems as a whole and how organisms operate within the context of a broader ecosystem. So, for example, looking at across ecosystems globally and drawing out specific design patterns. So things that we see consistently in nature that we might be able to draw into our design patterns and approaches in the built environment. So in nature, we see things like self-renewal and repair. We see a lot of closed-loop systems with waste recycling and reuse. We see an ability to adapt and evolve. So these principles are things we can learn from in engineering as well. And even looking at how we measure our performance. So in ecosystems, we see that performances can be measured by regenerative ecosystem services that are generated. So what if we started to measure our cities against a benchmark of what how an ecosystem would perform in that place? You know, how what services and benefits an ecosystem would deliver. It's a very different way of thinking about urban design.
It really is. Thanks, Sam. So when we think about that opportunity suite of benefiting from thinking about nature in our designs of cities and our critical infrastructure, I think the challenge and the opportunities there for the engineering community and the built environment community together to create those win-win optimal solutions is really substantive. It's super important then that we can, in a methodological way, in a rigorous way, take that inspiration from nature and turn it into a process of inquiry that leads us to solutions that are really holistic in their considerations and beneficial in their outcomes. So having nature as a context guide us in strategies for responding to that complexity and uncertainty is very exciting, and also we need to be rigorous in that approach. So today, hopefully you've been able to learn from our short discussion around what biomimicry is, what it looks like in an engineering context, and how it might contribute to the design of resilient cities and their component infrastructure. Thank you.